In the years we've been doing DataSceptic, I've had several interviews highlighting the major impact deep learning has had on both computer vision and natural language processing. Those are flagship areas where deep learning has had a big impact. But we've also heard about deep learning for weather prediction and lots of other tasks, too. Today continues that trend as I interview Ravi Krishna about neuroarchitecture search and its application to the problem of click-through rate prediction.
Hi, I'm Ravi Krishna. I guess the work was done as a collaboration between Berkeley and Facebook when I was a student at Berkeley and when I was also an intern at Facebook. But my affiliation right now is, I guess I'm working on a stealth mode venture.
Well, the paper I invited you on to talk about is differentiable NAS framework and applications to add CTR prediction. So there's a couple really interesting areas to dig into. Maybe to start with, could you define what the CTR prediction problem is?
Sure. So CTR, I guess first of all, stands for click-through rate. So CTR prediction basically involves predicting the probability of someone, a particular user online, clicking on a certain ad in a certain place at a given time. So you can kind of think of this like if you see any like sidebar ads online, right, or in ads in any position, really, deciding which ad to show you is really a very complicated problem for any internet company because they have a huge inventory of potentially millions of advertisers that want to show an ad there, and they need to decide what's the best ad to show to maintain a good user experience as well as to maintain the monetization for their service. And so what ads CTR prediction does is you build a very large-scale model that takes in user data and data about the advertiser, data about the specific ad, and about their interaction, and you try to estimate what's the probability that there's going to be a click on this ad or, some other action potentially. And based on that, you can rank which ad you want to show in that spot at a given time. And basically, this is what allows you to personalize ads online. Obviously, there's some more complexities with respect to ad auctions and everything, but this is the essence of the problem.
Why doesn't just the highest bid go straight to the top?
Yeah, so you could have a system that does that. If you did that, though, what would basically happen is, whoever has the largest ad budget would basically win every ad spot, right? And that's not necessarily a good thing from the user experience perspective because let's say some company XYZ is just a much, much larger company that have just a way bigger ad budget and they can outbid everyone else. Then you're never going to give an opportunity for other advertisers to get their products out there. And the users are not going to be so interested in your content anymore because all they're going to see is the same ad over and over again. So the relevance is really an important part of delivering these ads.
Well, you talked about having some data about the ads themselves, which if I go and set up an ad at most places, it's an image and some text maybe and a link. It's all unstructured data, but at least you've got something. With the user, there's no, intrinsic thing behind maybe their ID. Is perhaps you're tracking other things or storing stuff. What are some of the features you have to work with?
Yeah, features can range from very simple to very complicated. I think one of the features that's been actually discussed in published literature is, for example, just the number of clicks on this ad that have already happened, right? So if there's a lot of clicks on this ad, then that gives you some indication that it's relevant, right? That this is something people are interested in. That's a very simple feature, and it's very intuitive to see how it would be useful. But, there's also more complex features that you can imagine. Obviously, I can't speak about anything that's in production or not, but, what things you could imagine are like interest groups that you might associate a user with. So for example, is this user associated with like ice cream? Are they interested in buying ice cream? Are they interested in cars? Things like this. And based on that, you have a certain interest that the ad is wanting to target. So, obviously, if you have a car ad and someone is interested in buying a car, then, that's a match, right? So those kinds of cases are things that you could easily turn into features. As for where the data actually comes from, the ad data, I would say a lot of it comes from the interactions that have already taken place with that ad. And obviously the user data, it varies by service. You can imagine that obviously Google would use pretty different features than Facebook and so forth because their services are just structured differently. But it's basically all about matching the most relevant ad to the user that is most interested in that content.
And historically, how have people tried to approach this problem algorithmically?
Yeah, so this field has a pretty rich history, I guess. From a historical perspective, the best place to start is sort of collaborative filtering, right? And that's not really an ad-specific approach, but it's more like saying if I have, interacted with some set of products online, the typical example that's used is e-commerce, right? Or book recommendations on Amazon, something like that. If I've interacted with this set of books, what books have other people that have also interacted with those books? What are they interested in? And that allows you to recommend similar items. I think over time that has evolved I'd say in maybe the early 2000s, logistic regression was certainly an option that was used in production. But, the scale of all of these systems is quite large. It's grown over time, but, even 15, 20 years ago, Google was operating at a very large scale. And maybe in the last 5, 6, 7 years, depending on the company and the team, people have started to adopt these new sort of deep recommendation-based approaches that have drawn on the deep learning research community, which, sort of started in the image processing and convolutional networks, but it's obviously grown exponentially since then. People have adopted these techniques for ad prediction. The entire objective has basically stayed the same, predicting the probability of a click or of some other action, but architectures have become, more and more complex and more large.
Well, deep learning is certainly having a bit of a revolution and helping in a wide area of fields, so it makes sense to just kind of de facto try it everywhere. But is there something more to it? Were there aspects of like collaborative filtering that didn't work so well that you thought deep learning could be the right solution for?
Yeah, so a lot of models today for recommendation systems that are deep learning based have a few key elements in common. And this is sort of, I think, also described in the paper. One of the major ones are these so-called embedding tables or sparse features. And what those allow you to do is to represent very, very detailed information about a user or ad as a dense vector so that it can be processed by a network. So for example, one of the features you could imagine, right, that would be very natural is the user ID. Who is the user, right, that's looking at this ad? Now, that feature can be represented in a number of ways, right? In logistic regression, you could just do a sparse logistic regression where you have basically a one-hot encoding, right? You have 0 for every user that this user isn't and 1 for the user that it is. And then you have a bunch of weights assigned to that. That's one approach. What embedding tables do is they basically associate a unique vector with every user. And that could be a dense vector of some dimension, but the way that you represent the user's information as a vector allows you to pass it through neural network layers. And that is a major advantage because it allows you to compute interactions between all these features much better than existing approaches. So I think that's one major reason that deep learning has been adopted is because you can compute much more complicated interactions between these features than with prior approaches.
That makes a lot of intuitive sense and seems like it would be a step forward. Can you also, in some interpretable way, see that manifest in the model you train?
Yeah, so there has been work that's basically been looking at kind of how do you organize the structure of a recommendation system to optimally kind of get the information between the interactions of these features. And there have been a couple of papers that have centered specifically on that. So one that's quite well known in the community is called the Deep and Cross Network, which came out of, I think, Stanford and Google. And so that one, basically, the entire paper is about creating a novel layer type called the cross layer and combining it with existing fully connected layers. And what the cross layer does is, not getting into the math details, but basically it has a very efficient way of representing interactions between these features. And what the authors found was that you could add a couple cross layers to a series of fully connected layers, and it would significantly improve the performance. And there's a limit to this, as you would expect, because, for example, it'd make a lot of sense that, second order interactions between features would be very useful. But if you start going to like fifth and sixth order, that may be meaningless, right? And they did actually find that that happens in practice. So you can sort of see it in how these various models perform.
So there's a number of deep learning type approaches in addition to the one that's contributed in your paper. I guess we can compare them by accuracy in the traditional machine learning way. Are there other metrics, though, that we might want to look at considering we're going to run this at scale?
I guess one thing to say about recommendation systems is that accuracy really has a totally different meaning than in other applications of deep learning in one major way, which is that the sensitivity to the accuracy numbers is really on another level. Typically, what you do for CTR prediction is you measure log loss. So it's like a binary cross-entropy loss. And so, for example, on the Criteo dataset that we work with, those numbers might look like 0.44 something, right? Or 0.45 something. And what's interesting in this field is that people measure these numbers with extreme accuracy, and it's not hard to see why. It's directly correlated to revenues at these companies. But for example, the Deep and Cross Network paper stated that an improvement of 0.001 in log loss is considered commercially significant. So that's, I think, just one major statement to preface this whole discussion with. Accuracy is really measured in extremely fine increments. In terms of other metrics, commercially, when you deploy this, so not in a research environment, I guess there's kind of two things that you might want to look at. And I think there was a paper from Twitter that discussed this. So one of them would be revenue per, 1,000 impressions or something like that, 1,000 ad impressions. And obviously, that's a direct metric for any company. And another metric might be click-through rate, right? And the reason you need to look at both is because you could increase your revenue immediately, right, by just serving more ads. Those ads will on average be less relevant, but they would still increase your revenue overall. The problem with that is that because users will find them less relevant over the long term, they will engage with your content less. And so what that paper concluded is you got to measure both of these metrics. And generally, if you can improve at least one, either the revenue or the click-through rate, which is a proxy for relevance, then you ought to deploy that model. But if you're increasing your revenue at the expense of the click-through rate and the user relevance, that's a very hard trade-off to make.
Really good point. And that's a tricky, I guess, hyperparameter that a company's going to have to tune for its business needs.
Right. And that's where, yeah, as you said, basically the specific cases of the business will come into play in making that decision.
What about something like the compute time?
So aside from accuracy metrics, the compute time is a major element. I think generally the way this comes into play in these companies is you basically have a hard SLA, and that's the limit. So, whatever it is, whether it's in tens of milliseconds or hundreds of milliseconds, there's a number that's set, and that's set by, the teams that actually work on the business side of it, facing the customers and the users, and that's defined by user experience or the time you need to go to an ad auction or whatever. But that number is essentially a hard constraint, and generally speaking, you can't really go above that. So what you do as a researcher working on these models is you do the absolute best you can within that constraint. And so that's sort of what our work is about. It's about finding the most efficient and accurate architecture within a certain constraint.
Are there ways you can optimize for that? That's not something that I've ever found. I've worked with PyTorch and things like that. I can change out my loss function, but I don't see a clear way I can say, let me do this to be most efficient with resources. Is that a novel piece you have to build, or are there tools?
So that's kind of what neural architecture search is about, right? Or at least that's how we've applied it here. So neural architecture search, or NAS in general, is about finding this architecture that is best to optimize some metric. And what we did in our work is we basically found an architecture that optimizes some combination of the log loss and of the execution time. So you can construct a loss function like we did and like many other works have done that combines these in some way and that represents a trade-off. And that trade-off is going to be set by your business use case, however that's defined. But by doing that, you can basically construct a single loss function that you optimize.
Cloud ushers in great potential. Today's data-driven organizations can innovate and fly higher and faster than before. Estrado is built for modern data teams. It's a cloud-native solution with direct access to all the power, agility, and scalability of the Snowflake Data Cloud. And with Estrado, there's no data movement, so your business reaps the benefits of enhanced data quality, boosting your competitive advantage, reducing costs, and improving decision-making business-wide. Because your insights are always up to date, Estrado is extremely useful as a rapid prototyping tool, further speeding up the time to value. Data teams can employ this time-saving capability for data prototyping, rapid dashboards, and building business application prototypes so you can test things in a rich, no-code environment. This means the time to value is reduced from hours or days to mere minutes. As a progressive data leader, you need the right resources to help your team and help performance levels soar. Find out more at estrado.io/dataskeptic. ASTRATO, estrato.io/dataskeptic. And you describe your work as an NAS framework. Can you describe more about that? How is it maybe a platform that can be leveraged in multiple ways?
Yeah, so when we were implementing this, we really wanted to do that in such a way that it could be useful to other people, basically. And at Facebook, sort of the thinking behind this was that there are a lot of researchers and engineers working on these models inside of the company. And, in addition to just being useful for our own research work, we wanted to be able to give people a tool that they could use to save time. And I think this is one thing about NAS that is not really directly quantifiable in a results table, right? If you build something that saves an engineer like 10 or 20 hours of time of hyperparameter tuning, that's time that they can directly use to work on more important problems or more interesting problems, or that they can use to learn more, right? And I think that's a very valuable piece of the work. So what we wanted to do was to make that happen as much as possible. So the reason we say framework there is because we've designed it in such a way, and it's open sourced, that people can very easily take this and add their own what's called supernets. And a supernet here defines a set of architectures and a set of deep learning operators that constitute the space that you're searching over. And so because you can do that, people can even use this for entirely different applications pretty easily. And what we provide that stays the same is the search manager and all of the utilities to run the jobs and manage the jobs and collect results.
So search is one way of doing this. You could also try and evolve them or maybe solve it with backpropagation or things like that. Why is search the right path?
Right. So maybe let me clarify the terminology. I guess all these techniques are referred to as neural architecture search. Ours is actually a direct backprop solution. So what we have here is a single supernet that's trained, and as you train that supernet, it basically represents a multitude of architectures in a probabilistic manner. And so each forward pass, you do what's called a soft sample from a distribution. And essentially what you're running in that iteration is some combination of architectures that you could generate. And over time, that soft sample is essentially annealed so that it gets closer and closer to a hard sample. So at the end of the search process, which is essentially one training of a very large network, you sample architectures from it that should be high performing. So the benefit of this approach is that it gives you the ability to explore a very wide space, but to do so without needing a huge, RL-style search process, which is sort of how a lot of these NAS techniques originated.
And then once you've got that trained or you found a solution, can you talk a little bit about how it performs at inference time?
So we kind of explored a couple dimensions in the paper. I guess the most interesting one was about compressing embedding tables. So I mentioned this a little bit earlier, that basically you use these embedding tables to store very detailed and personalized information about users or ads. And as a result of that, they can become extremely large. And it's not hard to imagine, right? If you have 1 billion or even 2 billion users and you store 128 dimensional vector, you already have hundreds of gigabytes of data there, right? And these models can potentially even stretch into the terabytes. And so this becomes an actual problem at inference time, because deploying this on hardware, GPUs are not really designed to store embedding tables that are this huge, right? They have some amount of HBM memory, which is some tens of gigabytes, but they're not really designed to store stuff in the terabytes. So there's all kinds of literature and commercial work on building systems to run these models. Not going to get into that, but basically a lot of what we focused on in the paper here was how to compress these embedding tables. And there's 2 ways we explored to do that. One of them is by compressing the dimension of those vectors. The other way is by basically deciding how many vectors to store. So, you can imagine that you have some ads that are clicked on a lot more, some users that interact with a lot more content. You can basically decide, do I really need to have a separate vector for this user or for this ad or for this feature in general, right? And in a lot of the cases you don't, and that can save you a lot of storage. And we trained a supernet to predict exactly that. When we evaluate this at inference time, it actually does give a significant benefit. We were able to compress a model roughly 10x. So basically the architecture with the minimum loss was 0.4442, and we compressed that by 15.1x, and it increased the loss to 0.4454. So, that is a commercially significant increase, and I don't think you could really probably deploy that model in practice, right? But I think this shows the promise of the approach, that we're able to compress a model by more than an order of magnitude, basically, just with this NAS approach. And, if you were an actual engineer using this, that's really something that could help you, right? Instead of you having to spend all of the time to manually decide how many vectors you want in each of these tables, this thing just does it for you. And yeah, maybe the results aren't perfect, but it saved you all that time, right? And then, of course, you can apply your expertise to improve it further.
Well, if we look the other direction from the point of view of your model, you can say the other models are an order of magnitude larger. What are they doing inefficiently that you're able to capitalize on?
So there's nothing inherently inefficient about the model. The thing is, basically, those models are not customizing the size of the tables to their data. So these tables can be used for a variety of features. User ID is the most obvious, but there's plenty of other ones that you could imagine, right? Even time zone could be a feature, for example, right? And that one has a very small number of choices, but these features have a huge number of alternatives, and not all of them are equally useful. So, the one that you would do to start with is you would basically look at every single alternative that has occurred in your data, and you would consider that a separate case, right? You would essentially just enumerate every single one, and that's what you would start with. If you do that, you're very likely storing vectors for feature cases that very rarely come up, right? And you may not need to do that. So that's really the inefficiency that we're capturing. It's basically storage that's not adding very much to performance.
So there's an attitude about machine learning that if I'm not too worried about my resources, just add as many features as I can. Within reason, if they're bad features, maybe the model will ignore them. I imagine, though, in this case where latency is a concern and there are other potential issues, we want to ship a small enough packet. Do I still need to worry up front about having a good, well-structured feature set that's somewhat minimized, or can I just rely on your approach like a post-processing technique to compress me down where I need to be?
Yeah, I think absolutely you still need to have a good feature set. And the reason for that, there's a couple. So one of them, as you mentioned, right, you need a model that is small enough. Our approach helps, but it's not magic. Features are really the lifeblood of your model, and your model is not really going to have much of a chance of figuring out stuff that you are not providing it in your features. And likewise, if you're providing it features that don't add much value, that's not going to help either. There's also an additional problem of if you're providing features that are very prone to overfitting, that can cause major problems. So, a lot of these embedding tables, right? These so-called categorical or sparse features, you're storing data that's basically, customized to every single category that can occur in your data. And that, as you can expect, is pretty prone to overfitting. And what we found in our work empirically on this research data set is that a lot of the benefit is that you're removing feature cases that were really contributing nothing except they were making your model overfit, right? So I do think it's still very important to have a proper feature set, because without that, your model is really stuck, right? You can do the best from an architectural perspective, but having a new feature that incorporates a new insight could potentially deliver way bigger gains than, all the architectural tweaking that you might try.
And where do you see the work going next? Are there ways to extend the approach?
Yeah, so we talked a bit about this at the end. So in recommendation systems, certainly we see this being applied to other models. So we focused on one particular model family, I guess, called the Deep Learning Recommendation Model, or DLRM, from Facebook. But, there's plenty of other model types that this could be applied to. And in particular, there's sort of an entirely different structure of models that are designed for sequence-based recommendation, like e-commerce recommendation. And Facebook One has one called the Time-Based Sequence Model, or TBSM. But there's many others from Alibaba and other companies. So we definitely see that this can be applied to entirely different classes of recommendation models. In addition to that, we hope that people might find the framework itself useful to apply to other problems.
Could we talk through what a rollout like that would look like if there was a listener who has maybe their own content network or something like that, and they wanted to see how this could improve upon their existing prediction systems that they can use for ranking? What would it take to get the system set up and running?
This framework that we have here is strictly research, obviously. This is not a production. You can't deploy what we're doing in production. All this is something that will take your model on an offline data set and allow you to improve it. So what you would do is you would clone our code. Then the first thing you would need to do is you need to implement your own supernet. And so for that, you would need to decide on a set of operators that you're interested in exploring. And I think a lot of people in the back of their mind already have a lot of ideas that they're interested in exploring. You just never get the time to pursue them because you're so busy with other experiments and deadlines and whatever else. So you need to decide on that, basically what your search space is for operators that you want to explore, and then you need to implement that. And that's basically a PyTorch script. You would also need to decide on your loss function, so the particular trade-offs of your application between accuracy and between loss, you would have to decide on that. You would also need to decide on your hyperparameters, so the learning rates, the learning rate decay factors, all this stuff. And that stuff, it doesn't probably get a lot of attention in the research literature, but it's very, very important to getting good results practically. So once you have that, you have a supernet, you have your hyperparameters, you also need to implement a final PyTorch script that just describes how your sampled architecture works, and you may have that already, right? If you're experimenting with such an architecture, this is what's used to instantiate the final architectures after they're sampled and they need to be trained on the dataset. There may also be a couple other miscellaneous things like data utility scripts and stuff like that, but that's basically the main thing. The main things you need are a supernet, you need a sampled architecture implemented, which you probably already have. Then you need to decide on your hyperparameters, essentially.
And do you have any observations from the training of your own model? What should one expect in terms of the rate of learning and when it converges and all those important details?
One of the most important things we learned is kind of a meta lesson, which is before you embark on a new search space at all, we mentioned this in the paper, but basically we would recommend running a random search of that search space. So, basically just write a bunch of choices, whatever, use a Python script or something to generate a random set of configurations. I think that's really useful because it gives you an indication of the potential, right? One of my co-authors, Bi-Chen Wu, he likes to say basically NAS isn't magic, right? It can't really find anything in your search space that doesn't exist. So running a random search basically will give you a very quick idea of whether there's some potential there. And I think also looking at the results will give you an idea of what operators you might think are more useful or less useful, and that'll help save time later. So that's one recommendation, I think, for any application of NAS. But in terms of the actual learning process, I think one thing that people should pay attention to is sort of the annealing rate. So I think I mentioned that a little bit earlier, that you have this soft sample that becomes more and more like a hard sampling of a single architecture at each iteration. So it is important to pay attention to how fast that's happening because it affects the training process. I think it's difficult to give any really broad summary of like how models will train because every application is different and datasets have different sizes. But yeah, that's what I would say generally.
Yeah, good advice. So when you want to benchmark this or get a sense of the empirical performance, are there data sets you can compare against?
Yeah, so the dataset we used is this Criteo Display Ads Challenge, and this is used a lot in the literature for recommendation systems and for ad click predictions. So this has about 40 million or so samples. So yeah, I would recommend using this mainly because there are tons of results that you can use to compare your own against. But there's also a much larger dataset from the same company, which is their terabyte dataset, and that has an order of magnitude or two more data points in it. So if you're looking for something that might more closely model a production environment, that might be more relevant. Other recommendation data sets, there's one from the e-commerce from Taobao that also seems to be used. And then there's a couple others, like for example, smaller ones like Movie Lens is one that's used. That's more of a collaborative filtering tailored data set. I think the Criteo data set is a pretty good place to start.
And when you finally got a chance to run your approach against it and see some performance metrics, can you tell me a little bit about how it turned out?
Yeah, so we found that basically all our models were meeting what we considered to be state-of-the-art performance. In other words, there was nothing fundamentally wrong with our architecture spaces, which was a good thing to see. But in terms of the improvements, I think I shared one of them earlier, which was we found this pretty large compression from cardinality search. So that was nice to see. We also found compression in the other search spaces we tried. They weren't as extreme. In embedding dimension search, we found some compression from the models. One interesting thing we did find in MLP search was basically the correlation between the loss and the efficiency metric that you're using may not be as strong as you think, which is to say that there may be models that are very inefficient that are just not accurate. You would hope that basically by increasing the size of your model, it would improve the accuracy, but we found that that's really not always the case. You can end up with just basically a bad model that is very large and yet also not very good at predicting anything. So that was kind of an interesting finding.
Well, where do you see this line of work going in the future? Are we going to see continued improvements in what CTR can do and maybe the quality and precision of the ads we're seeing? Or is there some ceiling we're eventually going to hit where ML is doing about as good as it can do?
I think that CTR is it's a very practical technology, right? I mean, it's quite interesting to me that there's a lot of research work on it, considering that it's a really practical technology, and it's in some ways, it's really closer to commercial than to research. It's hard to say if there's really ever going to be a ceiling, because with compute resources improving and with data access inside these companies improving, I don't think that there can ever really be a ceiling. I think what's likely to happen, certainly at a lot of companies, is that the resources that you'll need to be able to procure, there'll be a limit, right? There'll be an amount of machines that you can afford as a company to generate some results. And it's possible you could do even better with more resources, but there's really very few companies on the planet that have the resources to do that, right? And have the data sets. So I think there's let's say, a practical limit on how well CTR prediction can perform. But from a theoretical perspective, I don't know if there's a limit, but I hope not.
Makes sense, though, yeah. Ravi, thank you so much for coming on DataSceptic.
Thank you for having me.